Today's lecture will look at DC circuits and Kirchhoff's laws. Um, and the first one we'll look at is Kirchhoff voltage law, which will be in this video. First, let's review a little bit about the notation and the conventions. So remember, if I have a voltage drop across an EMF, that's a battery here. Here I have a battery in this piece of a circuit. It has an EMF, E, associated with it here, but I marked the two ends of it, A and B. And if I want to calculate the voltage drop as I go from A to B, that's the final dB minus the initial. So I'm going across this battery in this direction in path 1, which I dash line sometimes. And if I go in that direction as I go across the battery, the last sign I hit is positive, and I use the EMF, E, and then the last sign I hit is the positive sign. Likewise, if for some reason I was coming the other direction, across 2, and I would want to get the voltage drop as I go from B to A, well, again, once you've marked the polarity of the battery, the positive terminal and the negative terminal, the high potential side and low potential side, then the change in potential across it is just the final minus the initial. And if you look at this, the final final side A is lower than the initial side B, and so when I subtract this from a smaller number, a larger number, I get a negative. And so again, I would just write down whatever the EMF was, and these typically would be volts that would be specified there. And then as I move across it in the direction 2, the last sign I hit is negative, and that's the sign that I choose here. So usually when I talk about going across an EMF, then I'll write it as delta V across it is plus or minus E, the EMF. And again, this would be usually 12 volts or 10 volts or some numerical value. And then I use plus or minus depending on which direction I'm going across it. And always use the rule, use the last sign that you hit. Similar kind of thing, remember, for the resistor. We did this, I think, last time. The difference about a resistor is I have to have the direction the current's flowing through it, or I have to, if I don't know, then I just choose one of the directions, make a guess, and choose that for what I would call positive current flow in this direction. If I choose wrong, then by the time I get everything settled, I would find out that the value for I would get here would be negative, so that would mean it would be going in the opposite direction. But again, as I go from A to B, I always mark based on the direction the current or the assigned current is going through that resistor. Current naturally goes from positive to negative. It goes from high potential to low potential. Remember, they're like positive charges. It's moving, and the positive charges like to go to low potential. So delta V as I go from A to B is the final minus the initial. That's what we mean by the delta. And again, as I go across it, I know that the voltage drop is I times R, and I choose the last sign that's hit, and if I'm going from A to B, I get a minus. If I'm going the other direction, that's in the opposite direction of the current flow. Now, delta V as I go from B to A is the final minus the initial. I go from B to A, the final is VA, and the initial is VB. And again, I just write down IR since it's a resistor. And as I move across it from B to A, I use the last sign that's hit. Again, you have to assign the high potential side and the low potential side of the battery. But once you've assigned a current flow or know the direction of current flow, in either case, you can mark the polarity of the battery. And then usually I just write that as delta V across the resistor is plus or minus IR. I and R are the magnitudes of current and resistance. And then I put in the plus or minus sign as whichever one was the last sign I hit, depending on the direction I move across it. So same rule in both cases. We can use that to look at resistors in series. This is a pretty simple example. But I want to go ultimately from, I want to get the potential difference from A to B. Current is going through this part of this line of the circuit is all the same. That's really one of the characteristics of resistors in series is they will have the same current going through them, but they'll have a different voltage drop across both of them in general. But if I look at this, VB minus VA, I want to get delta V from here to here. That's just the final potential, the potential at B, minus the initial potential at VA. And now then I'll do something, I'll put an intermediate point, there's my middle point, M. And what I'll do is I'll subtract the potential at M, and I'll add it. So that doesn't add anything, change anything. Just added 0 in the form of minus VM plus VM. And then I'll regroup them in this fashion here, group VB with VM and VM with VA. And if you look at those, what that is the change in voltage as I go from M to B. From M to B is this one here. Because I just mean by this, I mean the final minus the initial. This one here is the change in voltage as I go from A to M. So as I go from A to M, it's the final minus the initial. And so these regrouped variables are delta V M to B, delta V A to M. And then I switch these two, I just change the order, put this one over here, put this one here, and I get something that's a little easier to remember maybe, is that the delta V from A to B is delta V from A to M plus delta V from M to B. And if you look at that, they start with the same letter A, they end with the same letter B, and this intermediate letter, the adjacent letters here, are that label that intermediate point. Well, using what we know about the resistors, if I have an assigned current flow in this direction, current always flows from plus to minus, and so this side's the highest side of resistor R1, and this side's the lowest potential side. Likewise here, current flows through resistor R2 from high to low. So once I have the direction of current, I can assign the polarity or the high potential and low potential sides of that. Now, the voltage drop from A to M, that's from here to here. Well, it's just I times R is just our current voltage relation. And as I go from A to M, the last sign I hit is minus. So I'd write plus or minus, and then I would choose the negative sign because that was the last sign I hit. Likewise for the second resistor, as I move across it, that's a minus sign. So ordinarily I would write the potential drop from M to B is plus or minus I times the resistance, the current going through resistor R2 times the resistor. And then again, as I move across it and going from M to B, the last sign I hit on that circuit element is negative, and so I choose the negative sign. Well, I plug both of these values in up here, and you get the total voltage drop here from A to B is delta V A to M, that's minus I R1, plus the voltage drop from M to B, and plus the minus is just the minus. I can factor out the minus, and I get a minus I R1 R2. Well, that is a lot like a single resistor, I call it R sub S, with the same current I going through it and the same potential difference across. And if you match these up, I times RS, last sign I hit is the minus. And if I choose RS to be R1 plus R2, I get exactly the same voltage drop across it. In general, you get the RS is R1 plus R2, etc. All the way if you have N of them. Well, let's look at a circuit here. And here I've got E1, R1, E2, R2. When I close this, I'll get a current flow, but let's think about it as being open for right now. And I've got this current flowing in this direction, and based on that current flow, I have a current going through one thing after another thing after another thing after another thing, and then getting here at B. So I want to calculate the potential difference in this situation from A to B, and that's going to be the voltage drop across E1, voltage drop across the resistor R1, voltage drop across E2, voltage drop across R2, and then I'm at V. So that's going to be the sum of those. And then I use our rules, plus or minus E1. Last sign I hit as I move in this direction is positive. I mark the polarity, long bar is positive, short bar is negative. Current flowing in this direction, so it goes from positive to negative. Last sign I hit is minus sign, so I choose the minus. Here I get the last sign hit is minus, so I choose the minus sign here. Go across R2, and the minus sign. And so I get this result. And now then, if somehow or another we connect those two, we connect A and B, or maybe just push this line over, make it the same point, well, if I start and end at the same point, then they have the same potential. Or if I connect them by a wire, there's no pressure drop, or there's no voltage drop, potential drop across a wire, and so A and B are at the same potential, so there's no difference, and so this becomes 0. And I find that the sum, the algebraic sum of all these voltages around this closed loop now, once that circuit is closed, has to sum to 0. And that, in essence, is Kirchhoff's voltage law. Yeah. Well, people call it Kirchhoff's voltage law. I've made it a rule. To me, laws are fundamental laws of physics, and this is really something that is not a law of physics necessarily, but comes from a law, namely conservation of energy. If you remember, if I move around this circuit, then the charge, and I start and end at the same point, then I can't have lost or gained any energy around, and so there can't be any energy change in the system. So this is Kirchhoff's voltage law really arises from conservation of energy. But statement of it, the voltage drop around any closed circuit loop, so a complete loop that's closed of a circuit, must be 0. So if you sum around any of these circuits, has to sum to 0. I usually write it like this, so a sum over plus or minus all of the EMFs, and a sum over all the resistors, the current during the resistor times the resistance, and then I choose these plus or minus signs with assigning the polarity, the voltage, high potential and low potential side, and then that algebraic sum has to sum up to be 0. So that's Kirchhoff's voltage law from a very fundamental perspective.